Good afternoon, students. We will begin with our today's lecture. We are looking into jump instructions, and in the last lecture we were studying CJNE instruction, compare and jump on not equal instruction, right? So we'll just revise it. I had stopped at this instruction last time. So the instruction is compare and jump on not equal, and the format is CJNE. Mention with whom you are comparing, destination, comma, source, comma, and mention where you are going to jump. That is a relative number. Just to revise, relative number is one signed number, and if the condition is true, how far you are going to jump. So CJNE, destination, comma, source, comma, real. It is a 3-byte instruction, and all the jump will require 2 machine cycles. And what is the type of jump? It is a short jump. And see, compare and jump on not equal is going to affect the carry flag. How is we will see now. Now comparison mean the output can be the number is greater than, or the number is less than, or the number is equal to. Correct? So what operation is carried out so as the comparison is to be done? Internally, a subtraction is carried out to do the comparison. Okay, and as the subtraction is going on, if the numbers are equal, the result will be 0. If the numbers are not equal, if the destination is greater than source, so the subtraction borrow will not be generated. If the destination is smaller than source, then a borrow will be generated. So compare and jump instruction is the only jump instruction which affects the flag. And which flag? The carry flag. Rest, no other jump instructions affects the flags. Okay, it's only CJNE affecting the carry flag. Fine, students. Now with the help of this carry flag, I can find out whether the number is greater than or smaller than. Correct? Whereas CJNE instruction finds whether the number is equal or not equal. Hope you all are getting me, right? So then when CJNE is executed, see what happens internally. It's a jump instruction and a 3-byte instruction. So the program counter gets modified by 3, PC plus 3, right? Why is this happening? All the jump instructions, program counter points to the next instruction. So CJNE is 3-byte, program counter will be pointing to the next instruction, which is 3 locations ahead. So the jump instructions are going to modify the program counter. So PC plus 3, and to this a relative number will be getting added. And what is a relative number? How far is the jump? I said 15 locations forward. So PC plus 15 is going to happen. 15 locations backward. It means PC minus 15 is going to happen. That 15 is one relative number. And that's how, if the condition is true, jump is going to take place. Okay, students. So what are the formats? See, we have 4 formats. Compare, the first 2 formats are comparison with accumulator. The third instruction format is comparison with registers R0 to R7. And the fourth format is comparison of the data byte in memory. So these are the 4 formats of CJNE. So we had seen this also. CJNE A, comma, direct, comma, relative. So the example is written ahead. CJNE A, comma, direct mean 35 is a memory address. Mention the direct address. And relative, it's FB. So the CJNE A, comma, 35 hex, comma, FB hex. So the comparison is done between accumulator and the data present at the memory location 35 hex. So the comparison is between accumulator and the memory data. And if the numbers are not equal, if the data is not equal, jump is going to take place at FB. What is FB? FB is one negative number. And if you find 2's complement of FB, you will get the number as -5. Is that okay, students? So CJNE A comma, if the number is not equal, what is going to happen? PC plus 3 minus 5 is where the jump is going to take place. Next, CJNE A comma hash 8-bit data comma relative. Example is CJNE A comma hash 55 hex. Now accumulator data is compared with the immediate data 55 hex. And where to jump? C hex. It means C means 12. And it is a positive number. See, the last MSB is 0. So if the data are not equal, jump is going to take place at PC program counter plus 3 plus 12. Because 0C is one positive number. The third example, CJNE R6 comma hash 55 hex comma B0 hex. Now see, B0 is, what number is this, students? B is 11, means 1011. And the ahead is 0. So 40, 0000. Mean B0 is one negative number. Okay. So if R6 data is not equal to 55 hex, the jump is going to happen backwards, since that's one negative number. Okay. And the last example, CJNE @R0 comma hash 55. The data which is pointed by R0 compared with 55 hex, and if it is not equal, jump is going to take place. See, I have written 0x12. It means 12 in hexadecimal. Correct. How much will it be in decimal? It will be 12 plus 6. So 20 locations ahead. Is that okay? So the last 3 instruction is some immediate number is compared with accumulator, or is compared with register, or is compared with the memory data. Whereas the first instruction, accumulator, is compared with the memory data. Okay. Now let us see one example in detail. So conditional jump, CJNE is a conditional jump. If the condition is true, jump takes place, or else microcontroller will execute the next instruction. Okay. So CJNE A comma 45 hex comma 06. So the comparison is between accumulator data and the data from memory location 45 hex. So if accumulator data is not equal to the data from this memory location, then the jump is going to take place. And while jumping, program counter plus 3 plus the number 6, whatever number 6 is written ahead, that gets added. So this is the new address where the controller is going to jump. If the numbers are equal, then the jump is not going to take place. Microcontroller will execute the next instruction. So look into the right hand side of the slide. CJNE A comma 45 hex comma 6 hex. This instruction is written at address 100. Okay. So at 100 hex, the instruction is written. How many byte is the instruction? 3 bytes. So 100, 101 and 102 are the memory locations required to store CJNE. So the next instruction will be at 103. So see here, students, at 103 we have the next instruction. So if the condition is true, jump is going to take place 6 locations ahead, and if the comparison is equal, jump will not happen. Microcontroller will execute 103 instruction. Okay. So now if accumulator is not equal, what is with respect to this example, what is the current program counter? See here, students, the current program counter is showing, the current program counter is having 100. That's where the CJNE is written. So it will happen 100 plus 3. So what 103, 6 is added. So 103 plus 6, 6, 7, 8, 9. So what is the address getting loaded in program counter? 109. So what is the new address? Right. This is the current program counter. Plus 3 will happen. It becomes 103. 103 plus 6 will happen. 109. So what is the new address? New jump address? 109. Okay, students. So when I say 6 locations ahead, so what is that address? Exact address? 109 is where it is going to jump. Okay. So if the comparison is not equal, microcontroller is going to jump to 109 instruction. And if the condition is false, microcontroller will execute 103 instruction. Right? Okay, okay. Let me go to the next. Now I told you all CJNE to find whether I have a larger number, or whether I have a smaller number. How do I do that? Right? So see, for example, it is written CJNE A comma hash 35 hex comma skip. And now see, students, whenever we write instructions, we do not give the relative number. Right? We don't do this headache. Whether the jump is 12 locations ahead, whether the jump is 12 locations back. No. What do? We give a label. Where do I want to jump? I just tell the label. And the label is given to the respective instruction. It is the job of compiler and the assembler to find the correct number. Okay. So normally when we write the instruction, we write it like this. CJNE A comma, with whom are you comparing? 35 hex. And where do you want to jump? Give a label. Skip is the label. Right. So the instruction is going to compare accumulator and 35 hex data. What is there in accumulator? I have assumed 56 hex. So internally what is going to happen? 56 hex minus 35 hex. Now in this subtraction, I will not get a borrow because 56 is larger than 35. So there is no borrow. The carry flag is 0. So I can conclude accumulator data is larger than the second data. On comparing the two data bytes, 56 and 35, accumulator is having 56. So there is no borrow. Hence I can conclude accumulator has a larger number. Correct? See the second example. CJNE A comma 82 hex comma and the label where you're going to jump. Skip. So comparison is between accumulator and 82 hex. Now accumulator is having 56 hex minus 82 hex. In this subtraction, the second example, I am going to get a borrow. 56 minus 82, there is a borrow. Carry flag will be set. Hence I can conclude the data in accumulator is smaller than the other. Is that okay? So write the compare instruction CJNE and check the carry flag. I have to do these two things to find the larger and the smaller number. Okay. So CJNE is going to find equal and not equal. But I want to find larger, smaller. So along with CJNE, check the carry flag. If carry flag is 0 mean accumulator is a larger data. If there is a carry flag set, it means accumulator has a smaller data. In this way, I can do the comparison. Okay, students? So see here. Let us take a particular example. Finding the larger number. So let me assume the data, there are 10 data bytes, 10 numbers. The 10 numbers are stored at address 45 hex onwards. So that's the memory address. This is where I have 10 data bytes. Correct? And I have to find the largest number from those 10 data bytes. Okay, and I think of using CJNE. Right? Now CJNE itself is not sufficient. I have to write CJNE as well as I have to check the carry. Jump on carry, jump on no carry. So with these two instructions, I can do this finding the largest. Okay. So let us assume you have taken first number in accumulator, that is 32 hex. Right? And the second data is 82 hex. Okay, so you have taken the first two numbers, 32 and 82. So comparison is CJNE A comma 45 hex data comma some label. So accumulator is having 32, right? A memory location is having 82. So there is subtraction done internally, A minus the data, and there is going to be a borrow. This will tell me, since there is a borrow, accumulator is smaller than the other number. Correct? On subtraction, if I get a borrow, it means accumulator is having a smaller number. What am I finding? I'm finding the larger number. So while doing this, I should ensure that accumulator should always have a larger number. Why? Because always the comparison is done with accumulator. CJNE A comma 45, CJNE A comma 46, CJNE A comma 47. So the comparison is always with accumulator, and I should store the larger number in accumulator. Correct? So if I get a carry, it means accumulator is not having the correct answer. And if I do not get borrow, it means accumulator is larger than the other. According to this, if there is no borrow, accumulator is larger. If there is a borrow, accumulator is having a wrong number. Okay. So then see here down, how will you write the instruction? So the first is CJNE A comma 45 hex comma the label skip. Correct? So just let me remove that skip label so that I can explain it. Okay, initially, why have I written here? I'll explain it later. Okay, so CJNE A comma some which number are you comparing? Data from 45x and skip. Now along with this, I need to check the carry. Right? I need to check whether there is a carry or whether there is no carry. Okay. Now, if there is a borrow, if there is a carry, it means accumulator is not having the correct number. The correct number is in memory. The larger number is in memory. Right? So get that number from memory and store it in accumulator. So see here, this is the instruction which is going to store the larger number in accumulator. When should this instruction execute? Only when there is a borrow. If there is no borrow, this execution should not happen. Okay. So MOV A comma 45 hex, the instruction should be executed only if accumulator is smaller and hence the borrow flag is set. It means what should be the jump instruction? Its opposite. MOV A comma 45 should happen when there is a carry flag set. Mean the jump instruction should be the opposite. Jump on no carry. Okay, students. But the point is, by selecting an appropriate jump, our code becomes compact. How to select an appropriate jump? The next instruction, see what condition it should execute. This instruction should execute when the carry is 1. It means the jump should be the opposite. Okay. So when there is a carry, jump will not take place. Larger number will be saved in accumulator. and then go ahead for the next comparison. Correct? But if there is no carry means accumulator has a correct answer. Accumulator has a larger number. Don't do this. Don't do the data transfer. Go for comparing the third number. Okay. So my point is CJNE along with the carry is used to find the larger and the smaller number. Okay, students. Now, JNC next, and here is the label next. Where should this label go? Correct? The skip label, where should I write? Right? Now, how to understand this? Out of this CJNE, it has two functions. One is the comparison and the other is the jump. Out of these two functions, I am using only one functionality. Which functionality? I am only using the compare functionality. I don't want the jump functionality. Correct? Right? Again, I repeat. This CJNE instruction is going to perform two functions. One is the comparison and the second one is the jump. Out of that, I am only doing the comparison function. I don't want the jump functionality. If I don't want the jump, it means this skip label is of no use. Correct? I don't want to do this jump. Mean this skip label is of no use. Whether the number is equal, it does not matter to me. Whether the number is not equal, it still does not matter to me. Just do the comparison and come here. Correct? Do the comparison and always execute JNC. It means even if this condition becomes true, microcontroller should execute JNC. And even if this CJNE condition becomes false, microcontroller should still execute JNC. Hope you all are getting me. If the numbers are not equal, still execute JNC. And if the numbers are equal, still execute JNC. So then, where is the skip label? Right? Where should I write the skip label? In any case, microcontroller should execute JNC. In any case, it should execute JNC. It means the skip label should come to JNC. And this is how you find the larger and the smaller. Hope you get me, students. CJNE along with JC, JNC gives you larger and smaller. Hope you all have understood, students. Okay, so let me go for the next. We have one more conditional jump, DJNZ, and hope everyone is familiar with DJNZ. Two functions, decrement and check, jump on no zero. So decrementing and jumping are the two functions. So DJNZ, whom to decrement, mention, and where to jump, mention. So decrements the source as well as source and destination is the same. Decrement the source by 1 and check if it is non-zero, the jump takes place. If it is 0, jump does not happen. So it is decrement by 1, source minus 1, and it is loaded back into destination. 2-byte instruction, 2 machine cycle, and it is a short jump. So how is program counter getting modified? 2-byte instruction, so therefore PC plus 2 plus where to jump, the relative number. Okay, so see a few examples. There are two ways to write DJNZ. So DJNZ Rn comma relative number. Rn is R0 to R7 register. Example DJNZ R5 comma some label. Instead of writing relative numbers, we write a label. So first the decrementing happens. R5 minus 1 and the number is stored back in R5. So source minus 1 and number is stored in destination. R5 minus 1 and it is stored back in R5. So first decrement and after decrementing check R5. If it is no 0, the jump takes place. Jump to the label skip. Okay. And the second format is DJNZ direct comma relative. Direct means give a memory address. So DJNZ 45 hex comma the label skip. It means the data from this 45 hex is decremented by 1 and stored back at 45. And if that answer is non-zero, the jump is going to take place at label skip. See here. The point is, you normally DJNZ is, where do we use? We load some count, keep on decrementing and check if it is not 0. So we used to keep the count in registers R0, R1, R5. But the point is, you can also load your count in memory. Your memory location can act as a counter. Okay, students. So DJNZ, your memory location can also act as a counter. That is what you should remember. Fine. So we will see one example. DJNZ R5 comma 6. What is it going to happen? R5 will be decremented. So look onto the left hand side of the screen. So R5 is decremented first. R5 minus 1, the number is stored back in R5. And then it is checked. Is R5 non-zero? Yes. Then the jump takes place. And how is the jump address? PC plus 2, because DJNZ is 2 byte. So PC plus 2 plus the number relative. So PC plus 2 plus 6. If the condition R5 has become 0, then the jump will not happen. Microcontroller will execute the next instruction. So let us assume, look into the right hand side of the screen. At location 105, we have written DJNZ. So DJNZ R5 comma 6. Decrement R5 and jump to 6 locations ahead. So when DJNZ is executing, so what will happen? 105 plus 2. So program counter PC plus 2 will become 105 plus 2, 107. And to this 107, 6 will be added. So 107 plus 6, 6 locations ahead, 7, 8, 9, A, B, C, D. So where is the jump address? 10D. Is that okay? Where is the jump going to take place? At location 10D. So decrement and jump on no 0. If R5 is non-zero, 10D instruction is going to be executed. That is decrement R5. But if R5 is 0, increment R5 is going to happen. And just for example, it's taken. Okay, so that was DJNZ. Right? So just remember, students, the point was, either you can have register as a counter or you can have memory location as a counter. Okay. And where is the jump? You just give a label. Okay. How far will be, this will be calculated. 6 locations ahead, 6 locations behind will be calculated by the assembler. Okay. So in your exam paper, they will give you some program and they will tell you if the jump is going to happen, if the jump condition is true, what will be the program counter address where the jump is going to occur. Okay, so calculate the jump address in program counter. So they might give you something like this program. Right, now let us go to the next instruction, and that is no operation, NOP. NOP, that's it. That's an instruction, NOP, no operation. It is a 1-byte-1 machine cycle. From the name itself, internally, none of the registers get changed. No operation. The only thing that happens is program counter increments by 1. Why? Because it is a 1-byte instruction. So PC plus 1 is what happens. And see here, students, whenever program execution is going on, program counter will always be affected. Program counter is automatically incremented when the program execution is going on. Okay. Now, why do you have such an instruction? No operation. If that is doing no operation, then why do you have such an instruction? That is just because, see, whenever you want to have delay programs created, delay program is, for example, LED blinking. Turn on the LED and keep it on for some time. So do nothing. Microcontroller should do nothing. It should only keep that LED on for some time. Okay. So how that is called delay. Turn on the LED and write a delay program. And what should the delay program do? Nothing. Just keep on spending clock cycles. Keep on executing such instructions which will do no operation. Correct. So NOP is where we use to generate delays. So one machine cycle mean to execute NOP instruction require 12 clock pulses. Microcontroller requires 1 microsecond time to execute NOP. So if I keep this in loop 1000 times, it means microcontroller will be spending 1 millisecond time. So 1000 times NOP executed mean 1 millisecond time will be spent by microcontroller. If you loop it more number of times, I will get 1 second and so on. Okay. Now, and one more use of the NOP is, see, whenever I'm writing an assembly language program, at the very first instance, I do not get to know what all instructions I should be adding. Right? I go on, I did write the algorithm. After algorithm, we did write the program. But there are many times it happens like some instruction is left to be included. So generally what the programmers do, they write some 10-15 lines and then they insert some 5 or 6 NOP instructions. NOP, NOP, NOP. Some 5 or 6 locations, the instruction is written NOP, NOP, NOP. Again, some 10-line program and some 5-6 NOPs are included in the program. Why this is done? So that later on, if you want to add a few instructions in between the program, I can delete the NOPs and I can write those instructions in between. That's how these NOPs are helpful. Okay, hope this is understood. NOP 2 uses, creating delays and right in between the programs to insert new instructions. Okay, students? Yeah. So that's where we complete DJNZ jump, conditional jump, unconditional jump, and so on. The next that we are going to study is, the next part of instruction set is call and return instructions, students. Okay. Now everyone is aware, where do we use this call and return instructions? Everyone is aware with a term called functions. right? We write functions in our program, right? What is a function? Anyone can just tell me what is a function? When do you write a function? Okay, just let me explain. Now, whenever a set of instructions, if I need it frequently in my program, right? There are some few instructions which I will require frequently in the program. Then instead of writing those instructions in the program repeatedly, I will write those instructions as a separate program, which we call it as a function. And whenever I need those instructions, we keep on calling the function. Correct? So function is a set of instructions that are required frequently in a program. Okay. Now, in high level language, that is C programming, Java, and all those, in high level programming, we call that as a function, whereas in assembly programming, we call that as a subroutine. Okay. That small program, we call it as a subroutine or service routine. Okay, students. And how does microcontroller execute that subroutine? It is with the help of call instruction. CALL, call. Okay. So functions are called as subroutines in assembly language program, or also called as service routines. Right? Henceforth, we will use the term subroutine. Is that okay? Right? So we have two varieties, absolute call and a long call. So these are the ones which will call the function. And RET, RETI, these are the two instructions to exit the function. Okay, RET stands for return and RETI stands for return from interrupt. So call is going to execute the subroutine and return is going to exit the subroutine. Okay, students. So these are important instructions. We will see them tomorrow. So students, thank you. Thank you for attending and see you in the next session. Okay, students. So bye. See you in the next session.